To our next speaker. Veronica Romanek, or KD2UHN, is a Scranton graduate and is currently at Virginia Tech for graduate school. Let's give her a warm welcome.
All right, hello everyone, and thank you, Rachel, for that nice introduction. So like Rachel said, my name is Veronica, and I'm a student at Virginia Tech. So a brief overview of what I will be addressing today is what are SuperDARN, WWV, and the Grape Personal Space Weather Station? How can we use them to study traveling ionospheric disturbances? I'll go over an analysis of the data I've collected with the Grape, as well as the data I've collected with the SuperDARN network. I will compare the data, and then, of course, future work and conclusions. So to start things off, SuperDARN is the Super Dual Auroral Radar Network, and as implied by the name, it's a network of over 30 high-frequency radars. They extend from the mid-latitudes up to the polar region, and they're used to monitor the plasma motion in the ionosphere. The data that I'm working with in this presentation is from the radar located in Blackstone, which is pictured here, and then on the bottom you'll see an image that shows the coverage of that radar. So I'm sure many of you have heard of WWV, but just in case, WWV is a National Institute of Standards and Technology time standard station. It's located near Fort Collins, Colorado, and it outputs extremely accurate frequencies on all the ones listed on the screen, and the data that I'm working with is from the 10 megahertz signal. I'm also working with the Grape Personal Space Weather Station, which again, I'm sure you're all very familiar with. The data I've collected is from the Grape version 1, which is pictured here on the screen. And what it is a small measurement platform that can be used to make ground-based observations of the space environment. And it was designed by folks here at Case Western. So what I'm using these tools for is to study what are known as traveling ionospheric disturbances, or more specifically, medium-scale traveling ionospheric disturbances. These are characterized by wavelengths of 50 to 500 kilometers and periods of 15 to 60 minutes. And I'm using HF radio waves to do this, as you'll see throughout my presentation. So what I have here is a map that shows the location of WWV, which I'm using as a transmitter. WWV, as I mentioned, I'm using the 10 megahertz signal, so transmits 10 megahertz, refracts off the ionosphere, and then was received by the Grape located in or near Scranton, Pennsylvania. And here is an overlay of the coverage of the Blackstone radar in comparison to the path that the radio wave is roughly taking from WWV to the Grape receiver. I wanted to include this to show why I'm specifically using data from the Blackstone radar, and that's because the coverage overlaps with where I'm monitoring the ionosphere from the Grape system. So a brief overview of what I found working with the Grape data. So each day, the Grape outputs a file that shows the Doppler shifted received frequency, so how much the received frequency is deviating from the 10 megahertz transmitted signal. And I filtered that data using a low-pass filter. And then I performed a power spectral density. So basically, in the red boxes on the bottom, you'll see some oscillations. Those oscillations are characteristic of MSTIDs because they have periods between 15 and 60 minutes. And basically, on the top, you'll see some bright yellow spots. The bright yellow spots just mean that there were stronger oscillations detected in the data. So what I did is I looked at 2 years worth of data and I broke it down into seasons. So a season is characterized by the respective equinoxes and solstices of each season, and I took each of those days and I looked at a month before and a month after that day, and I called that a season. So after that, I averaged the power spectral densities for that entire season to just see what are we seeing in a more comprehensive picture. And so here I have the results I got from 2021 and 2022. And you'll see that there's some pretty bright spots mostly around sunrise and sunset. So the faint sloped line going across is the solar zenith angle, and the horizontal line going across is nautical zero. So where they intersect is considered roughly sunrise and sunset. And so you'll notice that a lot of the bright spots are concentrated around those times. And I wanted to see what are we seeing outside of that, specifically in the local night. So what I did was I zoomed in on hours from about 20 Central Time to 5 Central Time. The reason I'm working with Central Time is that's the point, the time zone where the radio wave is roughly refracting off the ionosphere. And you'll see that it's actually fairly active in the night. So my next thought is, how does this compare with other data sources, and what can we see? So as I mentioned, I'm working with data from the SuperDARN system. And so here I have an example. So this plot here in the red box is outlining a medium scale traveling ionospheric disturbance. You can tell that by the enhancements in the slant range power. So the bright red spots and then the closer to blue spots that kind of look like a wave, that is what I'm calling an MSTID. We can determine different characteristics about the disturbance from looking at this. For example, a negative slope indicates that the disturbance is moving towards the radar. And so what I did was I went through about 3 years of data, and I manually looked at every hour, and I looked, do we see these wave-like disturbances in the data? Yes, I would mark that down as a 1, and no, I would leave that as a 0. And then I summed up all those averages. So what I'm showing here is just my preliminary results. I kind of tried a few different things just to see what I could gather from my first run through of the data. So this right here, I'm just gonna show all of what I found to you guys. So this is just the general totals of the MSTID events from 2020 to 2022. I do want to point out, and as you'll see in a few slides from now, some of the data I didn't have access to. The radar just wasn't collecting data for small time frames, so I decided to break this up a little bit more to kind of get a more accurate picture of what we're seeing that wasn't skewed by any missing data. So here I have the monthly MSTID event totals for 2020. The y-axis indicates how many hours I saw activity for that month, and then of course the x-axis is the months. You'll notice that there seems to be more activity in the winter, which I found kind of interesting because studies have been done on large-scale traveling ionospheric disturbances that showed a similar kind of trend. This is the data I have for 2021. You'll notice I did not have access to data in October. And then 2022, and I don't have any data for August to November, but still you can still kind of see the trend. So I decided to compare this to my Grape data. So I broke it up in the same manner. So I converted all the universal times to central times so the axes matched. And then I summed up the hourly events looking at the same season. So the equinoxes and solstices in a month before and after each of those days. So they're each binned for the same time frame. And I was honestly kind of surprised to see this because if you'll see in the Grape data, like I mentioned, we're seeing enhanced periods of activity around sunrise and sunset. But when we zoom in on the night, we see that the night's fairly active. But this data from SuperDARN is showing that the daytime's fairly active. So I've stared at this for a long time. So what I kind of am thinking is that sunrise is roughly like a little after 5 Central Time, maybe like 7 or 8, and we do see the data kind of increases around that time in each season, and then again around sunrise and sunset. So I'm not sure if that's just me going a little crazy from staring at this for so long, or if that's actually something worth looking into. So then I did the same thing again for 2022. We see a similar sort of trend, but I was still a little bit surprised that it didn't match up more, because that's kind of what I was expecting. And then I compared all of my SuperDARN data, so 2020, 2021, and 2022. This is the most comprehensive data I have, so that's why it's off to the left. And so, yeah. So where do I go from here? So my next step is going to be working towards developing a method to animate the process of MSTID detection. So as I mentioned, I collected this data by manually scrolling through years of data, looking 1 hour at a time, and that's not the most time-effective way to do this, nor is it the most, I think, accurate. I think it would be good to work towards animating this to have a code notice when there's MSTIDs. I would also like to compare my results to other results for MSTID climatology developed with other methods. I also would like to eventually look into modeling possibilities. My thought right now is to look at the neutral atmosphere and maybe simulate this region to explore the interaction between gravity waves in the ionosphere, because gravity waves are believed to be a very strong catalyst for this sort of disturbance. And then, as we know, we're practically at solar maximum, so I would like to kind of examine the data that I'm finding with both the Grape and SuperDARN, compare that with the solar cycle, and see if there's any interesting correlations. So, a brief outline, just to review what I've gone over. So I'm using the Grape Personal Space Weather Station to monitor the 10 megahertz signal from WWV. I am doing that by looking at the received Doppler shifted wave. I'm also working with data from SuperDARN, and I'm manually going through every hour and looking for active or quiet hours. And then comparing the data and moving forward, I'm hoping to animate this process and work towards creating some models. I welcome any feedback anyone might have over the interesting results that I found. But otherwise, if anyone has any questions, I'm more than happy to answer them, if there's time.
Question about are you really looking at comparable data when comparing the SuperDARN to the Grape? And the reason I ask that is the Blackstone goes between central part of US all the way to northern Canada, whereas the Grapes are kind of lower latitude central. Could it be playing a role in the differences you see?
It could be. I haven't explored that. I could potentially look at more Grape data or kind of consolidate the Blackstone data that I'm working with, but that could be a possibility. I haven't looked into that.
I don't know. Does Blackstone is that an average of the whole?
I can comment on that a little bit. I do think that. So I did my PhD on traveling ionospheric disturbances observed by SuperDARN radars and Blackstone, and I was also Veronica's undergraduate advisor, so I actually know quite a bit about this. I do believe that the Grape and the SuperDARN data are going to be comparable in some ways. Most of the traveling ionospheric disturbances observed by the Blackstone radar are going to be in a region that is close to where the Grape data path that she was looking at is going to show. With that said, I think we do have to be careful at what times of day we look at, because when I looked at the data during the SuperDARN data during my PhD, I really focused only on the daylight hours, and that was because the quality of the ground scatter data in SuperDARN tended to be very poor at night, and I had a hard time seeing the traveling ionospheric disturbances in that way. And similarly, I also ignored dawn and dusk. So where you're not seeing things that match up with dawn and dusk in the Grape and SuperDARN, I'm not entirely surprised, because that was a difficult time to see in SuperDARN. I tended to ignore that. And then also, we've seen in the Grape data multiple presentations, starting with Steve Serwin's and then with Rachel Bodeker's, we've seen tremendous amounts of variability in the Grape data at dawn and dusk, which makes it a very interesting time period. Similarly, at night, there's the MSTID people, they generally classify things as daytime MSTIDs and nighttime MSTIDs, and they basically say they have different physics for various reasons. And so I think we also have to kind of look at that a little bit more carefully. I think that I think it's really interesting how the Grape could complement what SuperDARN sees and vice versa, because SuperDARN has certain better like spatial ways of looking at things spatially than the grapes do, but grapes have better maybe like they're more or less a continuous time measurement, where SuperDARN is measuring things once a minute. I think it's a really interesting complementary data set. And I just want to say that I'm really proud of Veronica for looking at all of this stuff and sticking with this, going through Scranton and then going on to Virginia Tech to continue working on this. And I think it's a fantastic job that she's doing. I also want to point out that she won one of the $25,000 ARDC undergraduate scholarships while at Scranton. And so I just want to say, I think I think your money was well invested to see her continue on in this way. So thank you, Veronica.
Thank you.